So welcome back, Level 2 physicists, continuing on with the atomic and nuclear physics internal, today looking at radioactive decay. Okay, so in the previous presentation, we discussed how basically isotopes undergo decay to become stable, and there's three major types of decay which we're going to look at today. And the first one is alpha decay. So basically in alpha decay, the unstable nucleus emits an alpha particle, which is made of 2 protons and 2 neutrons, okay, which is also known as a helium nucleus, okay, it's known as the alpha particle. And in terms of the missing notation, you will see that it will be, the mass has to add up, the mass number and the atomic number, so that means it'll be thorium 90, okay, and the mass will be 234, because 4 plus 234 gives 238, the mass number, and 90 plus 2 gives 92, the atomic number of uranium. They're quite slow and heavy, those ones. Okay, and then we have a beta particle, which is basically a high-speed electron, and sometimes a neutral neutron inside the nucleus is converted into a positive proton and a negative electron, and the electron is emitted from the nucleus. But you can see that the charge overall, at the beginning and the end, maintains the same value. Okay, it's basically no change in the charge. Then we have, again, beta negative decay, so the proton stays and the electron flies away, which we mentioned in the previous slide. The third type of decay is gamma decay, so basically an unstable nucleus with high energy is in the excited state. That's what that asterisk means. And that's released in the form of electromagnetic radiation or gamma radiation. Okay, high energy electromagnetic radiation, that's gamma decay. So in terms of the review, the proton is the 11p, okay, the neutron is the name of the 10n. We have the beta particle, which is your high-speed electron, and your slow-moving, heavy helium nucleus is 4-2He, which is the alpha particle. Okay, and note in nuclear physics, you don't really worry much about the charge. It's the number of protons and number of neutrons. So in terms of the properties of these particular types of radiation, the first point is ionization. So ionization is the ability of those particular radiations to ionize an atom, to pull electrons off or add electrons. Okay, so an alpha particle, being slow and heavy, isn't very effective in terms of moving, even though it is highly ionizing. So it's got the most ability to rip off the electrons. Okay, a beta particle has an intermediate ability to ionize, and essentially a gamma radiation is very poorly ionizing. Okay, so those are the three kind of properties in terms of ionization. In terms of being able to penetrate, however, because the alpha particle is so big and slow moving, about 0.7 the speed of light, it can only really basically get stopped by a piece of paper. Okay, so even though it's the most ionizing, the most dangerous, it's easily stopped by even the most simple, like clothes, basically. Whereas the beta particle, it's traveling a lot faster, it's a lot lighter, it gets stopped by a few centimeters of aluminium. And finally, the alpha part of the gamma radiation is highly penetrating, even though it's the least ionizing, and it can basically be stopped by about 2 to 3 centimeters of lead. Okay, it's the most penetrating of the forms of radiation. In terms of radiation deflection, the beta particle essentially in a magnetic field is going to be pushed up using Fleming's right-hand rule. Okay, the gamma ray just goes straight through because it hasn't got any mass or charge, and the alpha particle, being slow moving and quite heavy, has quite a lot of momentum, but it goes down in a magnetic field coming out of the screen. And then we also have a deflection in an electrical field. The beta particle, being negative, is pulled up, okay, attracted to the positive side of the field. The gamma radiation just goes straight through, no charge. and the alpha particle is also being heavy and slow moving, but gets pulled down to the negative side of the electrical field. So that there is a summary of alpha, beta, and gamma particles for you. So alpha particle +2 charge, beta -1, gamma has no charge. Alpha particle is a mass of 4, it's the most heavy. Beta particle is really light, and a gamma ray having no particle, so it hasn't got any mass. Penetration is about 5 centimeters in air for alpha, 30 for beta, and gamma just goes straight through air, has to be stopped by lead. The alpha particle is basically a helium nucleus, the beta particle is a high-speed electron, and the gamma radiation is electromagnetic radiation, it's a wave. Typical speed of an alpha particle is about 0.7, 0.8 of the speed of light. Beta particles about 0.9 the speed of light, and gamma radiation being radiation, a wave, is the speed of light, quite fast. That's the notation there for the different ones. You can either use the notations, or basically the notations given for the beta particle can be the beta symbol or an electron, and the same for the notation for an alpha particle. It's either a helium nucleus or an alpha particle. Alpha particle is strongly ionizing, beta particle is weak, and gamma radiation is fairly weak, but the advantage is that even though alpha particles are highly ionizing, they don't move very far because they're absorbed by paper or your skin, whereas beta particles are absorbed by a few millimeters of aluminium, and basically 2 centimeters of lead will stop gamma radiation. That's kind of a summary. And the mass always adds up. The mass and proton numbers at the start of the nuclear reaction always equal the same, as you can see from the equations there. Okay, and in terms of remembering alpha and beta decay, in alpha decay, the mass number is reduced by 4, okay, because remember the helium nucleus is atomic mass of 4, and the beta decay, the mass number is going to be the same, because there's no change, because the proton is converted into a neutron and an electron, but the mass doesn't change. And in terms of stability, okay, basically the isotopes keep on emitting particles until they form a stable isotope. So in this particular case, uranium-292 goes all the way down to lead-206, 82. Okay, and that takes quite a lot of time, and that's how stability is basically maintained. So you really want a large number of neutrons in the nucleus to buffer the protons in terms of stability. And you can see there what particles get emitted in order to get the stability of the isotopes.